Today, we want to talk a little bit more about double integral. Remember that the challenge here is describing the set over which we're integrating. The integral part is just saying what we plug into the expression, f of xy dx dy. That is height times area. And the integral is telling us what values of x and what values of y to plug in, or the other way around, what values of y and then what values of x to plug in. So notice that we've been spending most of our time just describing the region, because that's the big new thing. Today, we want to start evaluating some of these double integrals. Here's what we want to start with. So we're going to start by practicing evaluating our double integrals, but we're going to start with something very simple. I want to look at the integral from a to b of the function 1 dx. Going to go back to a function of a single variable, and we're going to integrate the function 1, the constant function 1. If we integrate the function 1 dx, the antiderivative of 1, or an antiderivative of 1 is just x. So we'll take x and evaluate that from a to b. We plug in b, we plug in a, and then we subtract. No problem. Here's what we want to notice. B minus a, what we want to notice is that b minus a is the length of the interval over which we are integrating. When we integrate the function 1, we get the length of the interval over which we integrated. When we integrate the function f of x equals 1, we get the length of the interval over which we integrate. The integral from a to b of 1 dx is b minus a. That's the length of the interval over which we integrate. This makes sense geometrically. Let's draw a picture of what's going on here. And if I've got the interval from a to b, and I integrate the constant function 1, if our function is constant, then we're just finding the area of a rectangle. So the height is 1, and the length is b minus a. Or I can say the length is 1, and the width is b minus a. When we integrate the function 1, we get to multiply. When we're integrating the function 1, we get to multiply. I'm pointing this out because this may or may not have been pointed out. We might have definitely calculated the integral of the function 1, but now we want to really think about integrating the function 1. Told us the length of the interval over which we are integrating. You think of it in terms of area, makes sense. So this idea we can carry forward. Let's take our double integrals and integrate the function 1. So the same thing happens, or a similar thing happens, if we integrate the function f of x y equals 1. The same thing is going to happen if we integrate the function 1 over a region R. Since our function is constant, we get to multiply. What our double integral is telling us is the volume under a surface and above a region in the xy plane. So if with that the height is 1 and the cross-sectional area always looks like the region, we're going to get the area of the region. So the integral, the double integral of the function 1 over some region of the function 1 dA will be the area of region R. So I guess it's not the same thing that happens. We didn't get the length of the interval because we're not integrating over an integral. So we get the size of the set over which we are integrating. So I guess instead of saying length of the interval, we get the size of the set over which we are integrating. Let's grab each of these double integrals and integrate the function f of xy is equal to 1. So here's a double integral. We have not calculated a double integral before. I have not told you how to calculate double integral before. Take a moment and guess what you would do first. Just use your algebraic instincts. Look at this expression and think, what will we do first? There's been a big hint because I said stuff like the last integral has to have constants only, the last integral can only use constants. I kept calling this outside one the last integral. So it sounds like we're going to treat these as parentheses and work from the inside out. So if you were thinking the first thing we should do is integrate 1 with respect to x, then that's exactly right. The first thing we're going to do is the first thing that we could see happening to the 1. Integrate with respect to x from y squared to 9. So first, we're going to take care of this dx integral. The integral of 1 dx is x, and then we'll evaluate this from y squared to 9. So we plug in the 9, we plug in y squared, and subtract. Now, this was just that first integral, the dx integral. We haven't done anything with the y integral. It's just sitting there. Waiting to be calculated. Now we're at the y integral. We'll integrate with respect to y. Before we just blindly go ahead and calculate this integral, let's take a look at what we're integrating. We're integrating from 0 to 3, 9 minus y squared. If we look at the integral, the area up here that we were looking for, this is supposed to give, this double integral is supposed to give of 1, is supposed to give the area of R2. And that's exactly how we would calculate the area back in single variable calculus. I could have asked this same question. We take the top function minus the bottom function, 9 minus y squared from 0 to 3. This is the single variable integral, or one of the single variable integrals that we would have set up to find the area of the region R2. Now we can do our second integral. Now we're integrating dy, so the integral of 9 dy is 9y. The integral of y squared dy is 1/3 y cubed. And we're going to evaluate from 0 to 3. So we're going to plug in the 3. We'll plug in the 0 and subtract. So I got 27 minus 1/3 of 27. So what's that, 18? Now, this is not how we would have set up the problem last semester, because we have a function of x and we can integrate this function of x. Also, we have two double integrals that are supposed to give us the same thing. So we should verify that those two double integrals do in fact give us the same thing. So our other double integral is the integral from, once again, we're going to integrate 1. And this one is going to be the dy dx integral, 0 to 9 and 0 to square root of x. So notice that in this integral, the first integral is going to be the dy integral. Once again, treating these like grouping symbols, first to integrate dy, then integrate dx. So here we're just going to be integrating dy first. Here is our first integral. So the integral of 1 dy this time is going to be y again. And we'll evaluate from 0 to the square root of x. So we plug in the square root of x, we plug in 0, and we just get the square root of x. We still haven't integrated on the x, so we'll integrate from x equals 0 to x equals 9 dx. And at this point, we land on the integral that we most likely would have set up. Because I'm just trying to find the area under the square root of x between 0 and 9. This is just an attempt to find the area under the function square root of x from 0 to 9. The problem was set up with the curve defined as a function of x. This is the most likely thing we would have done. If I had put this problem on a test, no one would have done the y integral. But now we can take care of the second integral. So our next integral is the square root of x. So that's going to be an x to the 1/2. So we'll have a 2/3 x to the 3/2 evaluated from 0 to 9. Plug in the 9, plug in the 0, and subtract. We have 9 to the 3/2. I don't know what 9 to the 3rd is, so I'll do 9 to the 1/2 is 3. Cubed is 27. Times 2 is 54. Divided by 3 is still 18. So we're good. That was disingenuous. I couldn't think of 54 right away, so I actually did the 27 divided by 3 times 2. So full transparency. Any questions? This is pretty good evidence that our double integrals are correct. First of all, we know that integrating 1 will land us on the area of the region. Second of all, this integral right here is the integral that would tell us the area of that region. Third of all, we had 2 double integrals that report the same answer. So that's pretty good evidence that we are right in this case. If you calculate, if you have 2 ways to do a calculation and they disagree, one of those ways is wrong. It's important to recognize you don't want to spend time now figuring out which one is right. They might both be wrong, but you know one of them has to be wrong. This is math class. We don't get to agree to disagree. Any questions? So we accomplished 2 things by doing this. First of all, we upgraded integrating the constant function 1 and see that will integrating the function 1 will give us the size of the region over which we are integrating. Integrating the function 1 also works for, say, a triple integral. Even though we haven't done triple integrals, I think I've alluded to the fact that they're coming. A triple integral would just be like a double integral times 1.5. We changed the notation a little bit because we don't want to use the same things, but W would be some set of X, Y, Z, some solid in R3, a set of X, Y, and Z. Because that's what we expect the integral to be telling us. Tell me what I should be plugging into this expression over here. This set of X, Y, Z, this particular set of X, Y, Z in this instance is going to be a solid because of the way we're describing for an integral. What's X between? We're saying X is all the stuff in between these two functions. Y is everything between these two functions. Z is everything between these two functions. That everything between tells us that W, this set of X, Y, Z, is going to be a solid in R3. We have a function f of X, Y, Z times dV. dV is just some small piece of that solid W. dV is some small piece of the solid W. And it works the same as the dA in our double integral. It'll be a dx, dy, dz. Or a dx, dz, dy. Or dy, dx, dz. Or a dy, dz, dx. Well, shit, I've got 4 of the 6. I might as well keep going. Or a dz, dx, dy. Or a dz, dy, dx. There are 3 of them. So we've got 6 possible orders that they could show up. But this idea of integrating the function 1 also applies to triple integrals. Although W is going to be the set over which we're integrating, instead of the size, when we describe the size of the set, since it's a 3-dimensional solid, we wouldn't be describing the length or the area, we would be describing the volume. So if we integrate the function f of x, y, z equals 1, dv, this will be the volume of the solid W. If we had a function of 4 variables, then we would just get the 4-dimensional hypervolume, whatever we call it. Integrating the function 1 gives you the size of the set over which you are integrating. So one of the things that we got out of this example is that integrating the function 1 gives you the size of the set over which you are integrating, be that a length, an area, or a volume. The other thing was that these double integrals can be done in parts, can be done in steps. Do the inner integral first, then do the outer integral. Here we had a function 1, so that was not much of an issue, but if we had the integral, a double integral, I don't want the square root x1. I want everything to be polynomials because it's early. The idea was that we could do the integrals in pieces. We can iterate the integrals. So these double integrals set up this way with a dx dy or a dy dx are iterated integrals. Earlier we had integrated the function 1. Here we have a function that's not 1, but it is a polynomial because if I have a chance to make my life easier, then I will take it. But we're going to do the same thing. I'm going to first deal with its integral dx. I'm going to integrate this with respect to x. The integral of x squared is 1/3 x cubed. Y is a constant factor. So I'll have a 1/3 x cubed times y. Y squared is a constant term, but we're going the other direction. We're integrating a constant with respect to x. So I'll get x times y squared. And then we'll evaluate this from x equals y squared to x equals 9. So this is still an integral. Oh, I have to plug in the endpoints. One of the things that we want to notice is that we're plugging x equals 9 and x equals y squared. So I'll plug in x equals 9 first. We're not plugging in for y. Y is just a constant because we're still in the land of x. So x is 9 times the y squared. That's plugging in the 9, and then we have to plug in y squared. This was just the x integral. We still have the y integral. Any questions? Everybody see the two integrals that we're working on. The other important thing to note is that we're plugging in y squared and 9 into the x's because we're doing the x integral. Now there's a lot going on here, so I'm going to make sure I'm going to take a few notes. So I had grabbed my calculator for this, and then I'm kind of embarrassed because 9 is a power of 3, and I'm dividing out of 3. So this is 3 squared to the third, so 3 to the 6th divided by 3, 3 to the 5th, which is 243. It's going to be 243. That's my y term. 9x squared, at least that's nice and civilized. Here I've got y to the 6th times what? So 1/3 y to the 7th. And I've got here y to the 4th. Oh, and it's minus 6. And then this is the function that I'm going to want to integrate dy, so I can plug in from 0 to 3. We have to decide what order we want to put things. Everything's out of order here, and I don't like it. We usually put plus c at the end, so I'm going to go from descending degree. So I'm going to have a integral of 1/3 y to the 7th. Negative 1/3 y to the 7th is going to be negative. Add one of the exponents, 8. So 1/24 y to the 8th. Next biggest term is minus y to the 5th. So minus 1/5 y to the 5th. Integral of y squared is 1/3 y to the 3rd plus 3 y to the 3rd. And the integral of 243y is 243 over 2 y squared, evaluated from 0 to 3. Questions? When you just write random polynomials to make your point, expect some weird fractions to show up. At least on this one, we get to plug in 0, so that's good. Any questions? There was a secret third thing that happened on this last example. The secret third thing that happened was when we write a double integral and we have it set up as an iterated integral dx dy, we typically don't write x equals and y equals on our integral symbols. We use the dx and the dy to tell us what's going on there. So even though this says from 0 to 3 and from y squared to 9, the dx says that this first one is the x equals, and the dy says that this outside one is the y equals. That was also pretty evident because this first integral has a y squared in it, so that must be the x integral. We don't integrate with respect to y, then plug in y. It ends up being like a whole being John Malkovich situation, and it's very confusing. It's actually not very confusing, it's just very weird. So I don't know if anybody's seen Being John Malkovich, but it's a thing. We absolutely could. We could write it as a dy dx, but that would change the integral, the integrals that we do here, right? If I wanted to write the dy dx integral, then I would have to go from 0 to 9 on the x and from 0 to the square root of x on the y. No, that's just how our definite integral, how the double integrals are set up. That last integral has to be constants. So if I just switch the dx and the y, and I put the y squared to y on the outside, then I'm not describing what I want. Because remember, this 0 to 3 is all the y's, and for each y, I want x to go from y squared to 9. I can't say that later. This y squared to 9 depends on a particular value of y. So the description that we have, the thinking that we have when we go to write the double integral is we do this outer one, say it's from 0 to 3, and then for a typical y value, what is x in between? For these y values, this is what x is in between. For these x values here, 0 to x, root x, that's what x is between. And that changes. I can't just say, go from 0 to 9 and then do the 0 to square root of x. So to answer your question, we can't quite do improv, yes, but we can do Dungeons and Dragons, yes, but we have to do other stuff. And that could be relevant. It might be that when we look at our function, the integrating with respect to x is not available. So if we have a function that was like, if we know there are some functions that we know don't have nice antiderivatives. Written e to the negative x squared as a dx integral, we can't do that. There is no antiderivative. So at this point, we would want to go back to our region, rewrite a dy dx and see if that helps. That's a hella contrived problem. This is not something that you'd be like, oh, this is going to happen all the time when we're working on the mission to Mars. That's not a thing. It's very contrived, but I just want to illustrate that you have to do. There's more than just switching the integrals. You have to re-describe the region. There's no homework after Lagrange multipliers because I haven't gotten around to assigning homework from chapter 16 yet. Because I don't trust computers to automate things, but really I shouldn't trust myself to automate things. So, all right, so that's double integrals. It's a game of what's x between, what's y between, with a few different rules. There were 3 things that we noticed today. Integrating the function 1 gives you the size of the region over which you are integrating. We integrate double integrals as iterated integrals, 1 variable at a time. And number 3, a notational thing. We use the iterated integral part, the dx dy, to tell us what these are rather than writing x equals and y equals, because that takes up a lot of space, and mathematicians are inherently trying to pull out all the things that we don't need to. That's it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.